This is 9.2 series and convergence, right? So recall in sequence, right? So we have definition of sequence when we have a list of numbers. Okay, so if I have the sequence is of n is 2, 3, 4, 5. Okay, or have a sequence b sub n is -2, 3, -4, 5, -6, 7, continue. Now, instead of in 9.1, we are looking at the limits. So that is, if you keep increasing, then what's the limit of the sequence? We look at the sequence from a different point of view. Instead of the term itself approaching something, we want to know the sum of these terms. In other words, think about this. If I'm going to add 2 and 3 and 4 and 5 and so on, what do I get? What should I expect to get? The sum. In this scenario, I think it's pretty easy if you see that you keep adding larger and larger number, that's simply blow up. So roughly it's infinite, right? It's getting larger and larger. On the other hand, for the second sequence, if you're going to add -2 and 3 and -4 and 5 and so on, right? Then what do I get? Well, that one is a bit hard to see now because you have negative and this, you got 1, so I probably cannot tell. So what happened is, if the sum of all the terms in the sequence add up to a finite number, sometimes end up to a finite number, then this sequence, right, has a sum that's finite, then we say the series converges. So let me give you a definition first. When I say a series, I mean the sum of all the terms in a sequence. If the sum of the series has a finite sum, the series is said to be convergent, otherwise divergent. Again, we're going to focus on the sum. Okay. So if we add all the terms of the sequence, we get these 1 plus a2 plus a3 plus dot plus a sub n. Now, with the summation notation, that's a sub k start at 1 and to infinity. Keep going. Now, the example that to show you again, sometimes you cannot tell. Well, sometimes, but most of the time, you cannot tell whether it has a finite sum or not. So, in order to do that, we're going to have to consider partial sums, right? So again, each of these are the terms of the series. The a sub n will be the nth term, right? The n term, that's the first term, second term, third term is n term. And to find the sum of the series, we need to consider partial sums. So if I write s sub 1, that means sum of the first one term. So just this one. If I write s sub 2, that means sum of the first two terms, a1 plus a2. A sub 3 means a1 plus a2 plus a3, so on. Or a sub n means a sub k from 1 to n, sum. So that means the sum of the first n term. So in order to determine the sum of all the terms in the series, we will look at the sum of the first n terms. then we're going to take n, well, let n go to infinity, then we can see how is it going to sum going to change as you're increasing the number of terms, right? So at the end, you're going to have the limit and go to infinity, and that will give you the actual sum of the series, right? So that's called the n partial sum. And if s of n has limit as n goes to infinity, then the series converges. Otherwise, it diverges. Right. Let's look at an example. What is the sum of this sequence, right? So the sequence formula is of n is n goes from 1 to infinity. Remember, this is the formula, okay? So what it means is here, the a sub n, what's this a sub n? It's n, okay? So what's a1? It's 1. What's a2? It's 2, right? Plug in a3. So that's pretty much the simplest formula that you've seen, just the n, okay? Now, what it means, if you're looking at the sum, right? So you're adding, first term is 1, second term is 2, third term is 3, fourth term is 4, plus, oops, plus, I continue, 5, 6, 7, equal, question mark, all right? So how do we do that? Well, this is example where intuitively you can feel, okay, so you kind of know the answer. You can add a larger and larger number, right, and go to infinity, right? So technically I can do it, so I know the answer is infinity, but beware that for the series and sequence in this chapter, a lot of time it's going against your intuition. So you think it's finite, but it's not. Or you think it's infinity, but it might not be. Or maybe adding 2,000. So probably the better way to do is you follow the definitions, okay? So I need to know the sum, the formula for the n partial sums. So what I mean is, if you look at, let's say, the sum of the first n term, I'll put it this way, if I ask you what's the sum of the first 100 terms, can you tell me the answer? Well, of course, you can add 1 plus 2 plus 3 plus 4 plus 5 up to plus 100 using calculator. It take you 5 minutes, you get the answer. Or maybe you say what's the sum of the first 1,000 terms. So we must have a formula to do that. Even in calculator, I don't think you can do it that fast. So recall in count 1. Actually, we do have formula for the sum of the first n integers. Okay, so if you forgot, if we have 1 plus 2 plus 3 all the way, n, right? So sum of the first n integers, it's equal to n times n plus 1 over 2. Okay. So, for example, if I want to know what is sum of the first thousands, 1 plus 2 plus 3 up to 1,000, then it's just 1,000 and 1,000 plus 1 over 2, right? So that really 500 there times 1,001. I should do the math. 500,000 500. Well, you can check the math there. But what I'm saying is we need to have the formula. So the sum of the first n term is n times n plus 1 over 2. Right, so that is the formula. Okay. Now, once I have the formula for sum of the first n term, then I'm going to ask myself, what happens when n goes to infinity? Okay, so the sum is really this, right? It's really sum of the first n term where n approach infinity. In this case, since I have the formula, what do you think in the limit of this quantity when n go to infinity? You see that the denominators go to infinity. Sorry, numerator go to infinity. Denominator stays same as 2, so that's approach to infinity. And now it's confirmed the answer we got is infinity. So this series diverges. And so we asked to determine whether it's convergent or divergent. The series diverges or is divergent. Okay. Now see that the way we do it here, it depends on this partial sum formula. So we must have the formula for the partial sum. We don't think it will get much harder to do. Okay. And so the answer is diverges. Right, so let's look at the second example. -1 to n power, and start at 0. This one, pay attention, and start at 0 all the way to infinity. All right, so let's write a couple of terms. Be aware that this start at 0 in this case. Let me be, but sometimes we start at 0, then 1, then 2, 3, and 4. So it's 0 in, -1 to 0 is 1. 1 in, -1 to the 1 is -1. 2, -1 squared is 1. 3 is -1, and then positive 1. So you see the pattern. All right, the term is 1, -1, 1, -1, 1. So you write out the sum. This is 1 plus the -1 and plus 1 plus -1 and plus 1. Let's continue on and on. Right, so what is the sum? Right, so again, this example is very tricky. Tricky because you might believe the answer is 0, right? 1 negative cancel, 1 negative cancel, 1 negative cancel. Again, that might be against your intuitions here. It's not 0 because when you say 0, you're assuming the number of ones and number of negative ones are equal. But don't forget that this list or the series here go on and on and on. Okay, so that's why again we must have a partial sum formula so it determines the answer. So what is the impartial sum here? What's the sum of first n terms? Now, if you look at this carefully, I probably don't have the very nice formula for the impartial sum, but I do have the do see the patterns here, right? So think about this. I'm going to raise it. Right, so what's this S of 1? Sum of the first one term Well, it's just this term is 1. The sum of the first two terms as 2. 1 plus the 1, 0. But the sum of the first three terms is 1. The sum of the first four terms, 0. 5 terms, 1. You see that? So the sum of the first n term can only be 1 or 0. Right? 1 or 0. And so I can write it in the formula this way. So the sum of the first n term can only be 1 or be 0. It is 1 when, how do I know it's 1? It's 1. 1 when the n is odd. And 0 when n is even. Okay, so then again, what is the actual sum gonna be? The actual sum will be the S of n limit and approach infinity. So as n's increase, right? Keep going, 5, 6, 7 billion trillion. Then the partial sum approach what value? Look at this again. A 1, a 0, 1, a 0, 1, a 0, 1, 0, 1, 0. What does it approach? Well, it just oscillates between 1 and 0, so it never, the partial sum never approach anything. So the limit here does not exist because it does not approach any value. And therefore, the series here also diverges. Okay, diverges. Now let's look at the next example here. So next example, I have n squared over n squared minus 1. Now this is a very different one. Most of the time you can see using the definition you find determine whether convergence is not efficient. So by that it means if you have to rely on the S of n, sum of the first n terms formula. When you're trying to do in this example, it's going to be a nightmare. Think about this. Start at 2. You put 2 in, I think we got 4/3, right? 4/3. The first term 2, and 3 in, I think you got 9/8. 4 in, you have 16 over 15. 5 in, you have 25 over 24. Now, each of the terms not too bad. But if you're looking at n partial sum, you're adding the first two terms here, adding first 3, adding first 4. All of these involve fractions, nasty fractions. And after you do the math, are we able to figure out the formula for the n partial sum? No, we can't. Right? We can't. So we're gonna have to have a way to determine whether the series converges or diverges without going through this process. Now, one thing you're looking at this example here, let me give some hint. So we have 4/3, right? And then we have what's 9/8, 16 over 15, 25, 24, and so on. Now, if you look at this carefully, each of these terms is actually bigger than 1, isn't it? Right, so this term is more than 1. That's more than 1. That's more than 1. That's 1. So although I don't know the answer, but I know that this is really roughly, it is bigger than roughly 1 plus 1 plus 1 plus 1 plus 1. And if you get 1, 1, 1, infinite many of them, you see then this is actually going to infinity. And this sum is more than that. So the sum here has to be getting huge, getting larger and larger. So it will approach infinity. And so this series would diverge as well. Diverge. And in fact, we're going to develop the first test to determine whether it diverges quickly. You see, it doesn't quite matter what we have here. As long as I look at the term itself, see these are the term. Let's say we have 1 here and then 10n squared at the bottom. Then if you look at the limits of this term, right, if you have 110, 10 here, the limit of this will n equal to infinity. Notice that the numerators, if you do the L'Hopital rule, so that become 1 over 10. So this term will approach 110. And because every term here is approximately 110, you have the sum of 110 plus 110 plus 110. Again, it's going to go to infinity, and it will diverge again. So my point is, as long as if you're looking at the term itself, if this limit of the term will n go to infinity approach something not 0, then the series will diverge. Okay, so that's called the divergent test. All right, so here's the test. All right, so this test called divergent test. If the limit of a sub n and approaching infinity not 0, then the series diverges. Notice that this is called divergent test. So you can only test whether it diverges, not converges. If you look at the example here, 3n plus 1 over 5 minus 2. So in order to determine whether it converges or diverges, one way to do is we look at the limit this general term. This is the a sub n, right? So a sub n. So 3n plus 1 over 5n minus 2 and approach infinity. Now I'll allow you to use a shortcut here if you know it from the Cal 1 algebra. Since the numerator and denominator has the same degree, okay, then the ratio of the leading coefficients will be the answers. In this case, 3/5. You can just look at the rule if you want to verify that. Since the limit is 3/5, it's not 0. Answers. The series diverges. Okay, see that pretty quick. Now keep in mind that again, limits is not equal to 0 and then diverges. If the limit is 0, you cannot determine whether converges or diverges using this test. Okay. Let's look at the next example. I'll skip this one. Here's another example. 1 over n times n plus 1. Now, you can see that this example here, what is using the divergence test again. How we do that, right? All you do is take the limit 1 over n times n plus 1 and approach infinity. Numerator stay the same, the number getting larger and larger, so that goes 0, so limit 0. Now, because limit 0, the divergence test doesn't tell us about whether the series converge or diverge, since it's equal to 0. So I cannot use that test. Now I'm going to use a different test. Anyone remember the partial fractions decompositions? Now, sometimes it's nice to rewrite these fractions as sum of two smaller fractions. So if you recall, if you have the function 1 over x and x plus 1, right, when we do the integrating this, remember? Then we do the partial fraction decomposition. See, first checking to see if that is proper. It is. Factor completely. So this will be written as two linear factors here. So one's x, one is x plus 1. So they are two linear factors. So with a and non-a being the top, right? So we basically do the same here. With the exceptions, for it's an integer n, but do the same thing. 1 over n times n plus 1 equal a over n plus b over n plus 1. Multiply both sides by the LCD, you got 1 equal a times n plus 1 plus b times n. Multiply it out, and you have 1 equal an plus a plus bn. Okay. What else? Then you can equate the coefficients, right? An plus bn on the right, no n's on the left. So that means an plus bn is 0, and the constant a, constant 1 on the left, so a has to be 1. A plus b has to be 0, so if a is 1, then b is negative 1, right? So when you got that, again, so that is really the same as 1 over n minus 1 over n plus 1, right? So when a is 1 and b is negative 1, you plug in. Now, the reason we want to do the partial fraction is because for this series, the partial sum is easy to do, okay? So if you think about this, what's the first term look like? Remember, this is your a sub n there. This is your a sub n, right? So what's the first term? Plug 1 in, so that's 1 minus 1 over 2. Second term, plug 2 in, so it's a half, minus the third. The third term is 1/3 minus 1/4, right? There's the fourth term, 1/4 minus 1/5, okay? So if you do the sum of the first n term, so adding these, 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 and these, and these, you're gonna see what? B negative half plus half, that's cancel, that's cancel. So lots of cancellation going on. All right, so let me write it down. Right, so plug 1 in, so that's the first term, that's the second term, that's the third term, continue, and last term n is the n term. So you can see negative half plus half cancel, negative third plus a third cancel, that cancel. So that one cancel with the term in front, right? So it must be negative, and then you're left with 1 over 1n plus 1, right? So the impartial sum is really 1 minus 1 over n plus 1. And then from here, you can find what the actual sum is, the limit of S of n, where S of n will n go to infinity. So what do you think? You can take the limit here and go to infinity. This goes to 0, right? Left with 1. So our answer is 1. Right, approach 0, so go to 1. So therefore, the sum of these terms is 1. And because the sum is 1, the series converges. Okay, so it converges to 1. Right. Converges to 1. Right, so again, this series is very special in the sense that when you rewrite the term as a difference of two terms or sum of two terms using partial fraction decompositions, the partial sum is easily computed because many terms got cancelled out. And therefore, I can use a definition, take the limits, and got the answer. This series is called a telescopic series. So here is the definitions. A telescoping series is any series that can be written in the following or similar form. See, there's a lot of b1 minus b2, b2 minus b3, and so on, in which many terms cancel with the precedings or following term. Okay? However, it doesn't have a set form. So what I mean is, you look at the bottom here, this series. It doesn't look like a telescoping series, but if you factor the denominator out, and then you're going to write partial fraction decompositions, it can turn into some of these form. So the partial fraction decomposition has to be used to put in the above form, and partial sum will be considered key because most term can be cancelled. Right? So that finished the first part of 9.2.